Wheels must be strong enough to support the vehicle and withstand the forces caused by normal operation. At the same time, they must be as light as possible to help keep unsprung weight to a minimum. Wheels can be made from pressed steel in two sections: the flange or disc that is drilled for the wheel fasteners, and the rim. Wheels can also be made from cast aluminium alloy. Alloy wheels are popular because of their appearance and because they are lighter than similar steel wheels. Aluminium is a better conductor of heat, so alloy wheels can dissipate heat from brakes and tires more effectively than steel ones. These are often called mag or magnesium wheels, but wheels made of magnesium are rarely used on road vehicles. Most wheels have ventilation holes in the flange so air can circulate to the brakes. Most passenger car wheels are of well or drop center design. This design allows for tire removal and fitting. Tires for heavy goods vehicles are much stiffer, but they can also be fitted to a well-based rim or to a flat-based detachable flange rim, depending on construction.
The tire provides a cushion between the vehicle and the road to reduce the transmission of road shocks. It also provides friction to allow the vehicle to perform its normal operations. Modern tires are manufactured from a range of materials. The rubber is mainly synthetic. Two types of tire construction are common: cross-ply and radial. Most passenger cars now use radial tires. And radials are replacing cross-ply tires on four-wheel drives and heavy vehicles. Tube tires require an inner tube to seal the air inside the tire. Tubeless tires eliminate the inner tube by making the complete wheel and tire assembly airtight. A special airtight valve assembly is needed. This can be a tight fit into the rim, or it can be held with a nut and sealing washers. Tires can be identified by markings on the sidewalls. This typically includes the maker's name, the rim size, the type of tire construction, aspect ratio, maximum load and speed, and in some cases, intended use. Regulations cover the allowable dimensions for wheels and tires on a particular vehicle. These dimensions are usually set out on the tire placard attached to the vehicle. Incorrectly selected wheels and tires can overload wheel bearings and change steering characteristics. The tire placard lists the wheel and tire sizes approved by the manufacturer for the vehicle. Using other wheels and tires may be illegal.
To ensure correct fit between a tire and rim, all manufacturers of wheels and tires comply with standard dimensions, as recommended by tire and rim associations. The width of the rim is the distance across the rim flanges at the bead seat. Its diameter is the distance across the center of the rim from bead seat to bead seat. The shape of well-based rims is provided by a letter code, such as J, K, JJ, KK. The width of the rim and the diameter is traditionally stated in inches. A rim designated 7 JJ by 14 would refer to a rim measuring 7 inches across the rim flanges and 14 inches in diameter from bead seat to bead seat, with the profile conforming to a JJ code. The rim width and diameter can also be stated in millimeters. Metric rims are not interchangeable with imperial rims. The tire must be an exact fit on the rim to fulfill a number of functions. It ensures that the narrow contact area between the beads of the tire and the rim will seal the air in a tubeless tire. It transfers all the forces between the tire and the wheel without slipping or chafing. It ensures the friction between the tyre and the rim prevents the tyre turning on the rim.
Wheels must be strong enough to carry the mass of the vehicle and withstand the forces that are generated during use. Some are made from steel. They're pressed in two sections, the wheel centre with a flange or disc that's drilled for the wheel fasteners, and the rim. They're then welded together. Others are made from cast aluminum alloy. Alloy wheels are lighter than similar steel wheels, and since aluminum is a better heat conductor than steel, alloy wheels dissipate heat from brakes and tyres more quickly than steel wheels. The wheel centre must accurately locate the wheel rim centrally on the axle. It must also provide the required distance from the centre line of the wheel to the face of the mounting flange. This is called offset. On this wheel, the offset is marked. It is 45 mm or 1 3/4 inches. Offset is important because it brings the tyre centreline into close alignment with the larger inner hub bearing and reduces load on the stub axle. This allows the inside of the wheel centre to be shaped to provide space for the brake assembly, usually located inside the wheel. Ventilation slots allow air to circulate around the brakes. In some cases, wheels are directional to assist the airflow. The rim must be accurately shaped and dimensioned and strong enough to support the tyre under the load of the vehicle and the forces generated by the motion of the vehicle. Passenger cars normally use rims which are of well-based or drop-centre design. The drop centre is used for mounting and demounting the tyre onto the rim. When inflated, the tyre is locked to the rim by tapering the bead seat towards the flange, or by safety ridges or humps close to the flange. In the event of sudden deflation or blowout, safety ridges prevent the tyre moving down into the well. This helps maintain control of the vehicle while it is being braked. Well-based rims can also be used on heavy commercial vehicles for tubeless tyres. The rims are referred to as 15-degree drop-centre rims because the bead seats are inclined at 15 degrees towards the flange. The taper gives a good grip and an airtight seal between the tyre beads and the rim. The low flanges and drop centre allow the special size, flexible tubeless truck tyres to be mounted and demounted in a similar manner to that used on smaller passenger car tyres. The stiff sidewalls of larger cross-ply tyres mean they cannot be mounted and demounted in this way, and many four-wheel drive and commercial vehicles use a flat-base, demountable flange rim. When all of the air is removed from the tyre, one flange can be removed so the tyre can be demounted. Wheels are fastened to the hubs by wheel studs and nuts. They are highly stressed by loads from the weight of the vehicles and the forces generated by its motion, and they're made from heat-treated high-grade alloy steel. The threads between the studs and nuts are close-fitting and accurately sized. All wheel nuts must be tightened to the correct torque, otherwise the wheel could break free from the hub.
A tyre provides a cushion between the vehicle and the road to reduce the transmission of road shocks. The air in the tyre supports the vehicle's mass, and the tread provides frictional contact with the road surface so the vehicle can manoeuvre for normal use. Radial ply tyres are usually manufactured in stages. The casing is initially formed by laying the rubber inner liner and the first layer of textile ply cords around a flat drum mould. The rubber-covered bead wire and sidewalls are then locked into position. The rubber sidewalls protect a finished tyre from curb damage and weathering. At the second stage building machine, the tyre is shaped. Belts of steel wire are guided into place. The tread is then positioned, and the uncured tyre is consolidated by rollers before it is placed in the mould. During the moulding and curing stage, the tyre is subjected to high temperature and pressure, and it takes on its final fixed identity with its own distinctive tread pattern. It is then trimmed and checked for balance and quality before it is inflated and run under load against a rotating drum. This is a final check for ride uniformity.
Two types of tyre construction are common: cross-ply and radial ply. The cross-ply tyre is the older form. It's also called a bias ply or conventional tyre. It's constructed of two or more plies or layers of textile casing cords positioned diagonally from bead to bead. The rubber-encased cords run at an angle of between 30 and 38 degrees to the centre line, with each cord wrapped around the beads. A latticed criss-cross structure is formed, with alternate layers crossing over each other and laid with the cord angles in opposite directions. This provides a strong, stable casing with relatively stiff sidewalls. However, during cornering, stiff sidewalls can distort the tread and partially lift it off the road surface, and that reduces the friction between the road and the tyre. Stiff sidewalls can also make tyres run at a high temperature. This is because as the tyre rotates, the cords in the plies flex over each other, causing friction and heat. And a tyre that overheats can wear prematurely.
Radial ply tires have much more flexible sidewalls due to their construction. They use two or more layers of casing plies, with the cord loops running radially from bead to bead. The sidewalls are more flexible because the casing cords do not cross over each other. However, a belt of two or more bracing layers must be placed under the tread. The cords of the bracing layers may be of fabric or of steel, and are placed at 12 to 15 degrees to the circumference line. This forms triangles where the belt cords cross over the radial cords. The stiff bracing layer links the cord loops together to give fore and aft stability when accelerating or braking, and it prevents any movement of the cords during cornering. The cord plies flex and deform only in the area above the road contact patch. There are no heavy plies to distort, and flexing of the thin casing generates little heat, which is easily dispersed. A radial ply tire runs cooler than a comparable cross-ply tire. This increases tread life. Also, a radial tire has less rolling resistance as it moves over the road surface. The sidewalls of radial ply tires bulge where the tire meets the road, making it difficult to estimate inflation pressure visually. It needs to be checked with an accurate tire gauge. Using correct inflation pressures extends tire life and is vital for safety. Sidewalls of an underinflated tire flex too far, which pushes the center section of the tread up and away from the road surface. This causes wear at the shoulders of the tire. In an overinflated tire, the sidewalls are straightened, which pulls the edges of the tread away from the road and causes wear at the center of the tread. A tube-type tire uses an inner tube, which provides an airtight container inside the tire. A tubeless tire is lined with a soft rubber layer to form an airtight seal. This inner liner also seals against small penetrations, letting air escape only relatively slowly. When a tubeless tire is fitted, an airtight valve assembly is used. It can be a tight fit into the rim or be held with a nut and sealing washers. A tire and wheel assembly must be balanced. As the wheel rotates, centrifugal force acts outwards. Any part heavier than the rest will vibrate vertically, with the heavy area slapping the road surface with each turn of the wheel. This is called static unbalance. Dynamic unbalance causes the wheel assembly to turn inwards and then outwards with each half revolution. As speed rises, rapid side movement of the front wheels causes a sideways vibration or wheel wobble effect at the front of the vehicle. These conditions must be corrected to prevent cupping or dishing of the tread and reduce tread life. Tread life can also be reduced by incorrect wheel alignment. The feathered edge of this tire indicates an incorrect toe setting, and wear on the one shoulder of this tire could be due to incorrect camber setting. Most passenger cars have tread wear indicators molded into the tread pattern. They generally provide an indication when the depth of a tire groove falls to 1/16 of an inch or 1.5 millimeters. Control of a vehicle in any weather conditions depends finally on frictional forces generated between the tires and road surface. On a dry road, a smooth rubber surface can provide a high coefficient of friction, sufficient to maintain a degree of control during braking, accelerating, and cornering. In wet conditions, the coefficient of friction between a smooth tire and the road surface falls to an extremely low value. Grooves in the tread pattern clear water away from the contact patch area. This allows a relatively dry area to be formed and for road adhesion to be maintained.
During cornering, centrifugal force acts on a vehicle to produce a side force. This side force must be resisted by the interaction of the tire on the road surface. The greater the side force, the greater the opposing force must be. Without this resistance, the vehicle will continue in a straight line. The pneumatic tire provides this opposing force by being able to distort while still gripping the road. Then, since the tire's construction makes it elastic, it exerts a force called cornering force, which acts between the tread and the road surface. It pulls the distorted rubber back to its normal position. The tire's sideways distortion makes the vehicle follow a path at an angle to the direction the road wheel is pointing. This is called the slip angle. As cornering force increases, so does slip angle. This vehicle is being driven into a turn with decreasing radius. Both slip angle and cornering force increase until a point is reached where the tire slides and the only resistance comes from sliding friction across the road surface. The tire grips again only when the vehicle has slowed or is making a turn with a larger radius. That is, when the side force is reduced to a level the tire can withstand without skidding. Since both front and rear tires develop a slip angle in a turn, the vehicle's path is determined by the steering of the front tires and the slip angles of both the front and rear tires. These slip angles depend on the location of the major components.
The center of gravity is the balance point of the entire vehicle. Its actual position depends on location of the major components. It is always located above the road surface and between the tires. When a vehicle is cornering, this is the point through which all centrifugal force is assumed to act. Its position is determined by the load carried by the front and rear wheels. That is, by how weight is distributed. This is a 40%, 60% fore and aft weight distribution. 40% of the weight is carried on the front wheels, 60% on the rear, and the center of gravity is closer to the rear than the front. a weight distribution of 60-40 has the center of gravity closer to the front than the rear. Lateral weight distribution can be expressed in the same way. The height of the center of gravity is determined by the height of the mass above the road surface. Every vehicle has static weight distribution, whether it is at rest or traveling in a straight line at a steady speed. This is changed laterally by centrifugal force when the vehicle is turning, and in a fore and aft direction during acceleration or braking. During cornering, centrifugal force puts more weight on the outside wheels. Acceleration puts more weight on the rear wheels. Deceleration or braking has the opposite effect. In a turn, centrifugal force tries to push the vehicle away from the corner. This is resisted by the cornering force of the tires. The tires have slip angles due to the cornering forces acting on them. And since the cornering forces at front and rear may not be equal, the slip angles at front and rear can be different too. With the center of gravity closer to the rear tires carry more of the weight, so they operate at a greater slip angle than the front tires. Larger side forces act on the rear tires, which causes greater tire distortion. This condition of higher slip angles at the rear causes oversteer. More weight on the front tires means they corner with greater slip angles than the rear. The vehicle is then said to understeer. With equal slip angles at front and rear, the vehicle is said to have neutral steer. Radial ply tires generate much higher cornering forces than cross ply tires, which is why the two tire types should not be used on the one vehicle. Slip is also influenced by inflation pressures, so manufacturer recommendations should always be followed.
Information on tire aspect ratio is now included in the sidewall marking, together with the type of construction and the speed rating. The speed rating of the tire is given by the letter code, which indicates maximum recommended speed for that tire. Common symbols for passenger car tires include S for up to 110 miles per hour or up to 180 kilometers per hour, H up to 130 miles per hour or up to 210 kilometers per hour, V up to 150 miles per hour or up to 240 kilometers per hour, and Z for over 150 miles per hour or over 240 kilometers per hour. Radial ply tires have always been marked with the section width in millimeters, but with the rim diameter in inches. For example, on this tire, 185 is section width in millimeters. 70 indicates a 70% aspect ratio. H is the speed rating for up to 130 miles per hour or up to 210 kilometers per hour. R indicates radial ply construction. 13 indicates the tire is suitable for fitting to a 13-inch diameter rim. Totally metric types are also manufactured. Here, 190 is the section width in millimeters. The aspect ratio is 65%. The speed rating is H, for up to 130 miles per hour or up to 210 kilometers per hour. R indicates radial ply construction. 390 indicates the tire is suitable for fitting to a 390 millimeter diameter rim. Metric diameter rims cannot be fitted with inch diameter tires, or vice versa. Although tire markings may remain traditional, say 255/45 ZR17, there is a worldwide move towards an ISO metric standard, which uses letters: P for passenger, LT for light truck, C for commercial, and T means temporary use as a spare wheel. The tire may have a load index number, indicating the maximum load a tire can carry at the speed indicated by its speed symbol, which follows the number. So a P-Series metric size code may read in full P205/65 R15 92H, P for passenger car tire. 205 is the section width in millimeters. 65 for 65% aspect ratio. R, radial ply construction. 15-inch diameter rim. 92 load index for a maximum load of 1,385 pounds or 630 kilograms, and H for a speed rating up to 130 miles per hour or up to 210 kilometers per hour. Further development of high-speed tires has expanded the speed categories to include W and Y. For this tire, Z indicates a speed over 150 miles per hour or over 240 kilometers per hour, but the load and speed rating is taken as the maximum load and speed. That is 89 for a maximum load of 1,275 pounds or 580 kilograms, and W for 165 miles per hour or 270 kilometers per hour.
One of the markings on the sidewall of a tire is a Uniform Tire Quality Grading, or UTQG grade. The tire's UTQG rating provides information on three aspects of the tire's durability and operational characteristics. They are tread wear, traction, and temperature. The tread wear number comes from testing the tire in controlled conditions. The higher the number, the longer the life expectancy of the tread. Since no one vehicle will be subjected to exactly the same surfaces and at the same speeds as the controlled conditions, the number can only be an indicator of expected tread life in normal conditions. The rating is based on a percentage of the projected wear life. For instance, a tire rated at 400 has a projected life twice that of a tire rated at 200. There are many factors that influence wear, such as vehicle speed, road surface, climate, vehicle wheel alignment, and the driving characteristics of the driver. As such, the rating can only be an indication of the anticipated wear characteristics of the tire in controlled conditions. A traction rating is a letter-based indicator system. The rating is based on the tire's ability to stop a vehicle on wet concrete and asphalt in a straight-line situation. It does not indicate the tire's cornering ability. The tire traction indicators are rated as AA, A, B, or C. AA is the highest rating. It is important to note that the test and relevant rating does not indicate hydroplaning resistance, dry or snow traction capacity, or cornering capability in wet, dry, or snow conditions. The temperature rating of a tire is a letter based on a controlled step speed test. The possible ratings are A, B, and C. The rating is a measure of how well the tire dissipates heat and how well it handles the buildup of heat. Excessive heat buildup can reduce tire life or even lead to tire failure. However, while temperature plays a role in the speed capability of a tire, it is not the only factor. It is important to remember that these ratings are based on standardized test conditions, and the tests do not reflect tires that are operated in overloaded, underinflated, and/or misaligned conditions. It should also be noted that when rated, one tire might be a low A and another a high B, so the actual operating performance differences might be relatively small. It is not uncommon for there to be differences in UTQG ratings within a given tire design. Sometimes, a particular vehicle manufacturer will require certain properties for the tires supplied to their vehicles, which can affect the ratings, both positively and negatively. Sometimes there are differences between small sizes and large sizes of tires in a given design. All of these aspects can affect the actual rating that is put on the sidewall. Tire materials have evolved with new combinations of elastomers, fillers, and oils, which determine the energy absorption capability or hysteresis level of the tire. This is one of the most important operational characteristics of a tire's design. Low hysteresis elastic compounds rebound quickly when deformed. High hysteresis elastic materials recover their original shape more slowly, which tends to increase friction forces, giving better grip even on wet roads. Elastomers include types of rubbers and polymers which have elastic properties. Fillers include types of carbon black and/or silicas. These provide dynamic reinforcement or energizers for the elastomers. Antioxidants and waxes are included to provide resistance from environmental wear, such as degradation due to the effects of ozone and oxidation from exposure to both sunlight and normal atmospheric chemicals. Manufacturers use a sophisticated selection process to create combinations that provide the required performance characteristics and hysteresis level of the tire. As a result, there is a direct relationship between the chemical combination and the operational characteristics of the tire. The rubber used in modern tires is mostly synthetic, with the elastomers and fillers added to increase strength and toughness. When used in the tread, this combination gives a long life. Natural rubber is weaker than the synthetic version and is used mainly in sidewalls. Early tires used cords of cotton, but with increased vehicle speeds and loads, rayon and nylon cords are now common. Cords of synthetic fabric have high tensile strength. They resist stretching but are flexible under load. The cords are placed in parallel and impregnated with rubber to form sheets called plies. Plies have high strength in one direction and are flexible in other directions. When cotton was used as a cord, the number of plies or layers in a tire was a measure of the tire's strength. Newer cord materials use fewer plies. A modern steel-belted radial with a 6-ply rating may have just 2 plies in its sidewall. Having fewer plies makes the tire more flexible. Higher numbers of plies makes a tire's response to bumps harsher. Some tires with particular applications have mono-spiral belt, or MSB, incorporated into their design. With this technology, a single continuous thread of steel is wrapped around the circumference of the tire, eliminating overlapping belts, seams, and joints. A mono-spiral belt tire is lighter than a tire with conventional multi-cross belt construction. It has more stability since it minimizes heat generation inside the tire and gives high shock absorption. The bead of the tire is made of a cord of high tensile steel coated with rubber. The end of the ply is wrapped around the bead, which is then wrapped in rubber to stop chafing of the plies and also to seal the bead against the rim. The length of the wire used for the bead determines the rim diameter of the tire. Belts that reinforce the tread area of the tire are mostly made of braided high-tensile steel wire, but they can also be made of rayon or polyester. The inner liner of a tubeless tire is made of soft rubber. The inner liner must be flexible and airtight. Tires generally fall into one of the following categories: directional, non-directional, and symmetric and asymmetric. Directional tread patterns are designed to provide a range of attributes during particular driving conditions. The tire can only be mounted to the wheel so that it revolves in a particular direction to correspond with the tread pattern. An arrow on the tire sidewall indicates the design direction of forward travel. Non-directional tread patterns are designed in such a way that the tire can be mounted on the road wheel for any direction of rotation. Symmetric tread patterns have the same tread pattern on both sides of the tire and can generally be classified as non-directional tires. Asymmetric tread patterns have a tread pattern that is different from one side of the tire to the other. They are designed to provide good grip when traveling straight and in turns. They are generally directional tires and must be fitted to the road wheel in accordance with the fitting instructions to ensure that they perform as designed under operating conditions.
The size of a tire must satisfy some basic conditions. The bead diameter must suit the wheel rim diameter. Section width must be suitable for use on the wheel rim and large enough to have a suitable load-carrying capacity for the vehicle. The overall tire size must allow sufficient clearance between the tire and the vehicle frame. All manufacturers mold information about the tire into its sidewall. In cross-ply tires, the bead diameter and the section width are stated in inches. For example, 600 by 16 indicates a tire with a section width of 6 inches and a bead diameter suitable for fitting to a rim which is 16 inches in diameter across the bead seats. The load capacity is indicated by the ply rating, for example, 6 PR. The aspect ratio of a tire is the ratio of its height to its width. It is usually given as a percentage. The lower a tire's aspect ratio, the wider the tire is in relation to its height. An aspect ratio of 98% means the section height of the tire is slightly less than the section width. This is called a cushion or balloon tire. An aspect ratio of 88% means the height is 12% less than the width, giving a lower profile. It is called a medium-low profile tire. The profile of cross-ply tires was reduced further to between 78 and 82%, called a super low section. However, the stiffness of cross-ply tires makes them unsuitable for further reduction in profile. Radial ply tires have been manufactured in 78% profile, but are also made with further reductions in profile, from 75% to 45%.
Space Saver spares are designed for emergency use only. They're designed to get you to a service center where you can have the regular tire fixed or buy a new one. When provided with the vehicle as part of the original manufacturer's equipment, most manufacturers warn not to exceed 50 miles or 80 kilometers per hour and 50 miles or 80 kilometers of driving on the Space Saver tire. Some cars are provided with miniature or collapsible Space Saver spare tires as spare wheels. These normally require a specially charged canister for inflation when being installed. Others have small temporary spare tires that are inflated normally with a compressed air supply, but to a much higher pressure than normal road tires.